Hello, and we're back to our online class. This is statistics class. We're talking about probabilities, and here we're talking about addition of probabilities. And there are basically two rules that you follow: the special rule and the general rule of addition of probabilities. The main thing is you got to decide where to use those rules. Once you make the correct decision, the rest is relatively simple. So basically you need to understand the question well, see what's happening, make the correct decision between these two rules. The rest should be relatively easy. And we use the special rules when the events that you are discussing are mutually exclusive. Remember, mutually exclusive events are the ones that can't occur, can't happen at the same time. If the events are mutually exclusive, you use the special rule of addition, in which case probabilities of a couple of events, A or B, taking place is a simple addition of separate probabilities of A and B. And the same applies to more events, 3, 4 or more events. Adding the probabilities for either A or B or C taking place, if these events are mutually exclusive, is simply adding the individual probability of A taking place plus the individual probability of B taking place plus the individual probability of C actually occurring. Now, let's have a look at our first example. Say you have a business where you sell mixed beans, broccolis, vegetables, and stuff like that, all packaged in a nice little bag. The machine mostly works properly, but sometimes some packages are underweight, some packages are overweight, and from time to time you run some quality assurance and check the packaging. You've recently checked, let's say, 4,000 bags, and this is what you've discovered. Out of those 4,000 bags, 100 bags turn out to be underweight, 3,600 bags turn out to be fine, satisfactory, and 300 bags turn out to be overweight. And the question is, calculate the probability of a bag being either underweight or overweight. So we have an addition of probabilities for these two occurrences, for these two outcomes. First, let's actually calculate the probabilities for each of these outcomes individually. And we're going to use empirical probability. The sum over here is, of course, 4,000 bags. And the empirical probability of a bag being actually underweight is 100 divided by the total number of checks, total number of bags, which is 4,000, so that's 2.5% chance. Copy that to the other outcomes, and we have 90% chance that the bag is fine, and 7.5% chance that the bag is overweight. Now, we want to see what is the probability of the bag being either underweight or overweight. With this kind of addition of probabilities, again, the first question you want to ask yourself is, okay, what do I understand about these two events? The main thing is whether they are mutually exclusive or not. And of course, the bag cannot be underweight and overweight at the same time. So these two are mutually exclusive, which means we use the simple special rule of addition of probabilities, where I just add the probabilities as they are. Again, what we got, as I said, is probability of the bag being either underweight or overweight is simply the addition of these two, because these two are mutually exclusive. The probability of the bag being underweight is 2.5% plus the probability of the bag being overweight is 7.5%. Together, that is a 10% chance, a 10% probability. Next, moving on to our special and complement rule. The complement rule can be useful sometimes when it's easier to find the probability of an event happening by actually first finding the probability of an event not happening and then subtracting that probability from 1. So in our example, if an event could be some event A, probability of A, it actually might be easier first to find probability of A not happening, say a probability of not A, or in a probabilities concept, we actually use this small tilde to denote the probability of no A, and then finding the probability of A by subtracting this probability from 1. And of course, for this to work, of course, you must have the events of A happening and the event of A not happening be actually mutually exclusive. Let's have a look at another example. Let's copy this data and let's complicate things a little bit. So in this data, we add one more row over here, really overweight bags. In this case, out of 4,000 bags, let's say 100 bags were really overweight, 200 bags were moderately overweight, and the rest as in the previous example. So let's say, for example, you want to calculate the probability of the bags being unsatisfactory. So basically, if you call this a probability of the bag being unsatisfactory, one way to do that is to add up all the probabilities that correspond to all the outcomes except the satisfactory one. But perhaps it's a bit time consuming. So using the complement rule, you can check the probability of an actual satisfactory bag. Let's call it P satisfactory, and subtract that probability from 1. In our example, probability of a satisfactory bag is 90%. So subtracting this probability of 90% from 1 gives you a probability of the bag being generally unsatisfactory, either over or underweight. That 1 minus 90% of the bag being satisfactory gives you a 10% chance of an unsatisfactory bag. And that is the complement rule for you. And lastly, we're going to talk about the general rule of addition of probabilities. But before we go into the general rule, first we need to define joint probability. Joint probability is a probability of two or maybe even more events occurring, happening at the same time. If we look at an example of two events, let's call them events A and B, then I will denote joint probability as P, A and B in the brackets, probability of A and B jointly taking place. So with this out of the way, the general rule is going to be that if the events A and B are not mutually exclusive, then the way we add probabilities is that we, just as before, do add the individual probabilities of event A plus the individual probability of event B taking place, and after that we still need to subtract the joint probability of A and B. The intuition is in the following example. For this example, let's say we have a survey of 200 tourists in Florida, and let's say this survey tells us that 120 tourists visited Disney World. I use DW for that. And let's say 100 tourists visited the Busch Gardens. I'll use BG for that. And let's say the question is, what is the probability that any randomly selected tourist visited either of these two places? If you forget about the general rule, if you use the special rule, what you'll find out is that the answer is kind of strange. The probability of a tourist visiting the Disney World, based on the empirical data over here, empirical probability is 60%. That's 120 divided by 200. And the probability of any random tourist visiting the Busch Gardens is 50%. That's empirical probability of 100 divided by 200. Now again, if you forget about the general rule, if you forget to check whether the events are actually mutually exclusive or not, if you just add these two probabilities as in the special rule, the probability that a tourist visits either of these two places is 110%. It's actually 1.1, but as you know, probabilities cannot be more than 100%. Probabilities cannot be more than 1. So the thing is that these two events are actually not mutually exclusive, which means we have to use the general rule rather than the special rule to add these two probabilities. And in our case, let's just say that the survey shows that 60 tourists visited both places. So the joint probability that A and B, both places, will actually be visited, empirical probability, that's 60 over 200, that is 30% chance. So coming back to our question, the probability of any random tourist visiting either of these two places is the probability of visiting Disney World plus the probability of visiting the Busch Gardens minus the joint probability over here, which gives you, of course, 80% chance. And lastly, let's have a look at one more example. Let's say you have a standard deck of cards that has 52 cards, just a regular deck of cards. And the question is, what is the probability that any random card that you pull out from that standard deck of cards is either king or a card of hearts? First question you want to ask yourself is, are these two events mutually exclusive or not? And these two, of course, are not, because the card can be both king and a card of hearts. That's king of hearts. There is only one card that actually is both of these. Even though it's only one outcome when both of these events actually take place, these two events are not mutually exclusive. So we have to use the general rule of addition of probabilities. So let's have a look at the actual numbers. We have a few outcomes over here. Any card that you pull out could be a king, and there are 4 kings in a deck of cards. Any card that you pull out could be a card of hearts, and there are 13 hearts in a deck of cards. And the joint probability that a card that you pull out is actually both. That's king of hearts. Such a card is only 1. And to find the probabilities of these, we divide these numbers by 52, because there are 52 cards in a standard deck of cards. And I simply copy these. So as you see, of course, this is not an exhaustive list of outcomes, but this is enough for me to calculate the probability of a card being either kings or hearts. The general rule is, of course, the probability of the card being either kings or hearts is the probability of kings coming up plus the probability of hearts coming up minus the joint probability. And that is probability of kings plus the probability of hearts minus the joint probability. That gives me 30.77%. Or generally, that's actually 16 out of 52 cards. 16 50 seconds. So there you go.